This is the awesome size of the universe, and we're going to have to take some time to go into some basics of cosmology. So this is going to be a basic sort of introduction, if you will. We're going to go through the basics, and then we'll get into the really cool stuff, like how the universe expands. But first we've got to learn some of these basics. And the first thing I want to show you is the Mount Wilson Observatory. This is where a lot of the great things took place in the early 1900s. Milton Humason was working here. You see a picture of the 100-inch Hooker telescope. The Mount Wilson Observatory just outside of Los Angeles, opened in 1917. It's still open, as a matter of fact, today. And you can go there, you can see where Humason collected all of the data that made him and Edwin Hubble famous. They actually were the first ones to document that the universe was expanding, and it's going to take me a little while to explain that, but let me give you some basics. First of all, Humason would sit up there at night in the Hooker telescope, and he would have to move his telescope as the star moved across the sky. With the Earth rotating, he had to be very careful to make sure that the telescope was always on the light he was collecting. Of course, it was could be miserable up there. He'd have to do it during the winter when it was cold, because they opened the observatory up to have the telescope looking outside, or if it was hot in the summer. And of course, he always had to make sure he went to the restroom and didn't drink Coke or anything during the night, because he couldn't leave. And Humason collected an immense amount of information, and Hubble then took that data and eventually published it, and we now have the famous Hubble constant and Hubble law, which we'll talk about very shortly. There's a picture here. Humason is on the very left, and then next to Humason is Hubble, Edwin Hubble, and then the person third from the right, and I'm sure you recognize him, is Albert Einstein. Now, the light that's being collected, what happens to that light when it comes in is it goes through a prism, and the prism splits it up. I'm sure you all know about prisms. Prisms break down light into various wavelengths, and if you take white light, you can break it down into red, yellow, green, blue, and all of those colors are associated with a wavelength. And we're looking now at the electromagnetic spectrum, and as you can see on there at the bottom, you have the radio waves, and you move on up through microwaves and infrared, and then you see the visible spectrum. And they were collecting data in the visible end of the spectrum. That is, they wanted to be able to detect what was happening to the light coming in. So they amassed this data, and you know, these stars are so far away that Humason had to make sure that that telescope was pointed on a star in order to collect enough light so that they could break it down and analyze it into the wavelengths. Now, how did they do that? Well, once you have a spectrum, you can take a look at the spectrum, and one of the things you're going to see is you're going to see black areas of missing wavelengths. We call those spectral lines. In this example, we've got an emission and absorption spectra for hydrogen and helium. Now, if you went out and you burned, let's say, a sodium lamp, that sodium is going to produce very specific wavelengths associated with that element. Each element is going to actually produce a different color when it burns or it's heated up. And that's because and I don't want to get into the details here, but it's because of the electrons. They get kicked up and then they fall back down, and they give off a very specific amount of energy that's associated with a very specific amount of wavelengths. And so, if you're looking at hydrogen, you have an emission spectrum which only gives off those wavelengths. If you're looking at the hydrogen, there's one big one in the red, there's one in the blue, a couple in the purple end of it. If you put them all together, you get the color green that you're seeing here for hydrogen. For helium, you can see the spectra are all across, the emission spectra are all across the board there, and you get the color of blue for helium. Now, if you have gas in the star, then you can get absorption. If there's hydrogen in that gas or helium in that gas, when the light comes from the star, those elements absorb light. And so when that light reaches Earth, those particular wavelengths, whatever elements are in that atmosphere, are going to be missing. And these are the spectral lines that you're seeing under the absorption here. And that tells us a number of important things, but the first important thing is that we can tell the composition of stars simply by getting and collecting data from them. Now, to go on and tell you a little bit more about the information they were collecting and how they were using it, I need to talk a little bit about the Doppler effect. You are probably aware of the Doppler effect because you've heard it. You may not be aware that it's called the Doppler effect. So let me play this sound for you, and we'll listen to it, and then you can, I can talk a little bit more about it. Now, what you heard was, you heard the sound of a car coming toward us, and then you knew, I think you instinctively knew when that car passed us where the car was, because you heard a change in the sound, and that's because of the wavelengths. Now, in this picture, I'm showing a car. That car is moving. Let's think about it stationary. If it's stationary, it's going to generate waves in each direction, and those waves will be the same. So a person standing at position B will hear the same as a person standing in position A. But as soon as that car starts to move, then it goes from position A, goes from away from person at B towards person at A. And what's happening there is, and you can see by these circles, that you're actually shortening the wavelengths as it moves towards person A, but the wavelengths are getting longer as it moves away from person B. So as a car approaches a person, the wavelengths are compressed. And as it moves away, the wavelengths get longer. And that's why you're hearing the change in sound. You're hearing the change in sound because as that car passes you, it's going from shorter wavelengths to longer wavelengths. Now, why go to all this trouble to show you this? Because we can see exactly the same thing with stars. When a star is coming towards us, it's making its wavelength shorter. When it's moving away from us, the wavelengths get longer. And that's what's described in this diagram right here. You're seeing that as the star is coming towards us, those wavelengths are shortened towards the blue end of the spectrum. And I'll show you a picture of it here in just a minute, but you can see it says blue shift on the diagram. The same thing is true, though, if the star is moving away, except that the wavelengths get longer. And as the wavelengths get longer, they shift towards the red end of the spectrum, and that's called a red shift. Now, why is that important? Well, I'm hoping that you can see that if we can collect the light and we can look at the spectra, that we can actually tell whether a star is moving away from us or towards us. And believe it or not, we can also tell the speed at which that light is moving. Now, on this slide, you can see on there hydrogen and potassium lines, spectra, the two lines, and they're close together, and they have what we compare this to is the sun. You can get a spectra from the sun. It's a stationary object. It's not moving towards us or away from us. So you can get that spectra, and then you can compare that spectra to other stars. So you can see a shift. If it's moving towards us, it's going to shift towards the blue end. In this case, the star is moving away from us, so it's going to shift towards longer wavelengths or towards the red end of the spectrum. And you know, when they first discovered this, we're going to talk about Vesto Slipher, but he was one of the first ones that calculated, or he was the first one to discover a redshift, and he was astounded at the estimates of speed that he was getting for these stars. This particular one is moving at about 1,200 kilometers per second away from us. That's a phenomenal speed. You could go around the Earth in a minute going at that speed. So he was looking at phenomenal speeds, which really shocked everyone in the early 1900s when they were coming up with these kinds of speeds for stars, you can imagine. Here's one at 1,500 kilometers per second, and they continue to go up, and notice that the potassium-hydrogen spectral lines go more and more to the right in each case, down to 60,500 kilometers per second. So you're seeing a shift in the spectrum, towards the right end, or the red end of the spectra, because each one of these stars is not only moving away from us, but it's moving faster and faster away from us as you go from bottom to top. And this is a little bit better example. This is the sun on the left with spectral absorption lines, and then a star is on the right, and you can see that it shifts from the left side to the right side. It shifts towards the red end of the spectrum. So this star is moving away from us, and the amount that it's shifted is equivalent to or proportional to its velocity. And that's extremely important. These red shifts in stars then can give us some idea not only about whether a star is coming towards us or going away from us, but also give us speeds. Now, one of the things that they noticed early on was that stars seem to be mostly anyway, moving away from us. Only a few, like our Andromeda galaxy, which is close by, it's moving towards us. So it has a blue shift. But most of the galaxies are not moving towards us. It just so happens that the Milky Way and Andromeda are within the sphere of gravitational pull, so they're pulling each other. Our galaxy is bigger than the Andromeda, so Andromeda is being pulled faster towards us than we are towards it. But there is a tug there, and it's quite significant. So let's now talk a little bit about the history and how all of this came about. You're looking up at the sky. This is the night sky down the middle of the picture here, and that's what you might see if you're out in the country on a night and you're looking up at the heavens and you're seeing the Milky Way going right down the middle of the sky. And it's a disk-like object. I don't know if you've ever noticed it, but it's not only full of stars, but it's full of gases. That's why you see those shadows in there and clouds. So there's immense amount of stars and gases in the Milky Way. And back in the early 1900s, when Slipher and Shapley, who we're going to talk about, when they were studying these, they thought the galaxy was our universe. They thought our galaxy was all there was. And of course, Hubble had to come along to realize that there was more out there than just our galaxy. And Vesto Slipher, that you see here on the left, he was the first man to recognize a Doppler, or I should say, to get a Doppler shift from a star. And he did that in 1912. And it was really a tremendous discovery. He did it at the Lowell Observatory, and the speeds, as I mentioned, that he got astounded not only scientists, but the public. Everybody was quite interested in this discovery. I guess it would be a little bit about like the Higgs boson has become today. And the man on the right, Harlow Shapley, he discovered, or he made a map of the Milky Way, and it was really the first map. And he could tell from that map that we have a galaxy. We're looking down the disk. We're actually on the outskirts of the Milky Way, and he could see immediately that there was a disk. And I've shown you a spiral galaxy down here on the left, much like our galaxy, and we would be out on the edges of that spiral galaxy if that were the Milky Way. If we could somehow get outside of our galaxy and look down on it, it would look a lot like the one you see in this picture. And we're on the outskirts, so when we look at the disk across the sky that is the Milky Way, we're looking in towards the center of the Milky Way. And oh, by the way, we now know there's a black hole in the center of our galaxy. We'll talk more about black holes. We use light years as a way to measure distance. It's not a time, it's a distance. So it's the amount of distance that light travels in a year. and so we call it a light year. Gives you some idea of just how astoundingly immense our universe is. Our galaxy is just one of billions of galaxies that are out there, and there are billions and billions of, in fact, there's about 1 trillion stars in our galaxy. It's a little bit bigger than most galaxies. So it's an amazing place. And Shapley was the first one to recognize just how amazing it was. Imagine back in the early 1900s when they were making these discoveries, how exciting it must have been. Well, the woman that you see here, her name was Henrietta Leavitt, and she worked at Harvard at the observatory there, and she was the first one to recognize that Cepheids, a particular type of star, had a very constant variation in the output of energy. And she was able to document that variation, and you can see in this graph here, it's luminosity versus time. And these Cepheids, they produce a certain amount of energy that varies, and as we'll be able to see here in just a minute, that variation in luminosity, if we can determine how that varies in the brightness of the star, and then we know how far away that brightness is, we can convert apparent brightness into real, true brightness, and then we can get an idea of the distance. Now let me take a minute and explain what the heck I'm talking about here. If we have a nearby light, it's going to have a true brightness when we're standing close to it. But the farther and the farther that light moves away from us, the less bright it's going to get. And we could, in theory, if we knew how bright it was, we could tell how far away it is based on the apparent brightness and the intrinsic brightness. We call the true brightness, the intrinsic brightness. And there's a way to mathematically relate this to things like luminosity. A lot of technical terms, no need to get into it that deep, but the key here is if we can tell how far away one Cepheid is, then we can use this distance ladder, so to speak, to keep measuring Cepheids in other galaxies, and then we can get an idea based on the apparent brightness of Cepheids and the knowing the distance to one, we can then tell how far away each one of those are. And that's what Hubble started to do in the 1920s. He started to take these Cepheids, and as soon as he knew how far it was to one Cepheid, he could extrapolate to other Cepheids, I should say. But it was a fellow named Hertzsprung that was the first one to measure a Cepheid distance, and he had to use the parallax method to do that, which is what you're seeing here. Now, I don't know if you're familiar with the parallax. We use it sometimes on Earth. If you're out on the ocean and you see something on shore and you know where you are in your boat, and you get the angle, the direction, and then you go and move your boat a known distance, and you look back and you get another direction, and you know the angles, then if you know the distance and you know the angles, you can calculate from trigonometry precisely how far it is to the object. And that's what's happening here. Hertzsprung waited till the Earth was at a particular position, then he sighted a star, then he waited for the Earth to go around the Sun, and he knew the arc on that, so he got the angle, and then he measured back and precisely, and then he was able to simply, with trigonometry, the tangent theta is equal to the opposite over the adjacent. So we know what the radius of the distance to the Sun is, or I should say, we know the distance to the Sun, which is a radius from here to the Earth, and that circle we're going around. So we know the opposite side, we know the angle theta, so all we have to do is take the tangent theta and calculate the adjacent. Very simple calculation in principle. It was not a simple calculation in terms of actually making the observations. It was extremely difficult, but Hertzsprung was very, very careful in his work. He came up with a very good distance